Now, before I talk a little bit about why cognitive computing is so important and where it's going, I'd like to just reflect for a minute on sort of how we got here really very, very quickly. In August of 2007, in IBM research at Yorktown Heights, we were looking into the future, as we always do, decades out, and we were looking at the explosion of data. Now, this was before the term big data had even been created. But we were looking at the trend, the exponential curve, the sort of what I call the next Moore's law of data, where it was doubling every 12 to 18 months. And not only was it exploding in volume, but it was exploding in terms of the variety and the lack of veracity of the data, the noisiness of the data. And we said, you know what? This is scary, because the computer systems that we have been building for the last 50 or 60 years are not equipped to deal with that mass of data or the amount of unstructured data that will be generated over the next decades. Well, we underestimated what was going to happen, but fortunately, as we were struggling with that problem, I'll never forget the day a meeting showed up on my calendar with the code name Blue Jay. Now, in IBM, everything is called Blue something. So I understood the Blue, I didn't understand the J. And in came a group of our researchers who had been thinking about this problem. And they proceeded to tell me about an idea they had to tackle one of the big unstructured problems in computer science around natural language understanding in the area of deep question and answering in open domain. And I said to myself, well, you know, that's one form of artificial intelligence, and don't you understand that we're in a winter of artificial intelligence? Decades have gone by where no progress has been made. What are you going to do differently? And they proceeded to tell me what they were going to build with a system now called Watson, and they were going to test this system on national television in the game of Jeopardy. And I said, I don't think so. Because at the time, the system was getting about 20% of the questions correct, and it was taking about an hour to answer one question. But long story short, the team went on to create a system that you all recognize in February of 2011 that was really the first public demonstration of a cognitive system, a system that could understand unstructured data and make sense of it and come up with recommendations and conclusions, not just a list of web search pages. And of course, it went on to great things. But just think about the time frame. That was August of 2007, and here we are less than a decade from that, and look at the things that President Jackson was talking about and things we're going to talk about today. The last comment I'll make is we did not set out, the team in IBM did not set out to create a replica of this. We did not set out to map the brain. We did not set out to build a replica or a form of artificial intelligence that replicated what humans do. We set out to tackle the simple problem of massive unstructured data, making sense of that and bringing insights to humans, not replacing humans. And I think that was really a breakthrough thought, because everyone else who had tried to do artificial intelligence had tried to replicate the human brain. So why is this important? And I've thought an awful lot about this, and I urge you to think this way. Don't just think about artificial intelligence and replicating the human. I think what this is all about is the price of not knowing, the price of not knowing. And as I hope to convince you, many of the answers to the things we need to know are in the data, but once again, our systems just cannot find answers to those questions. So let's talk a little bit quickly about the amount of data and how unstructured it is and how literally every industry and every human being is being swamped by this information. We see it in every industry. In oil and gas, the amount of data that's being generated through IoT, Internet of Things, sensors on these platforms is off the charts. Oil companies we work with tell us we have all of this data stored. we don't know what to do with it. We can't analyze those signals to know what's going on these big multi-billion-dollar platforms out in the ocean. Consumers, we are generating tremendous amounts of information in social media, Twitter, Facebook, et cetera. Mining that information is very difficult. It's in natural language or in things that don't even look like natural language in many cases. Understanding that, making sense of that is critical. If you're an individual, you want to understand what's going on. Can I get insights of what's going on in social media? If you're a retailer, you want to know what's going on there, because if you do not understand buying patterns, your supply chain, your inventories will be all out of balance at critical points in the year, and we see this all the time. In fact, this morning, we announced a new application on the iPhone, which is Watson Trends. We called it Inside IBM Secret Santa. It monitors social media and looks not only at what's currently being bought for the Christmas season, but what are people talking about that they may buy in the future. Trends that are happening in people's thought processes, and that's allowing individuals to buy ahead in a sense, but it's allowing retailers to anticipate what they need on the shelves during the heavy Thanksgiving to Christmas season. Appliances, again, Internet of Things, huge amounts of information being generated. Today, little, if anything, being done with that information. Healthcare. As President Jackson mentioned, in April, we opened a new business around healthcare because this is a exploding industry. It's an $8 trillion industry worldwide. Half of that $8 trillion is in the United States, by the way, and spend. And guess what? About a third of that is waste. A third of that $4 billion in the US is waste, not to mention the implications of bad diagnosis or errors in diagnosis. But the amount of information that's being generated on each one of us now throughout our lifetimes is off the charts, highly unstructured information. And in the area of security, the amount of information in cities like New York, London, Paris that are being generated from surveillance cameras, again, incredible amounts of information, some very minor amount of real-time analysis of that data, but by and large, most of that data goes into deep storage and doesn't get pulled out until there's an incident. Think about the cost of not knowing in Paris, the cost of not knowing in Paris. In the area of energy and utility, again, we've done a great job in places like the United States and portions of Europe instrumenting our homes with meters, smart meters. But again, that data lies dark, lies dormant. In fact, it's estimated that between 80 and 90% of the world's data lies dark. We don't use it, our machines don't understand it. Think about the opportunity in that 80 to 90% of the world's data. And then in the area of security, now billions of dollars are being stolen, whether it's intellectual property, personal records, bank accounts, health records. The cost of not knowing who's doing this and the cost of not stopping this is escalating again exponentially. Transportation, telematics, self-driving cars, once again, both an opportunity for those that can leverage this amount of data, but also, again, if it's not used properly, the safety threats that accompany not being able to deal with this massive amount of unstructured data. So I hope I've convinced you that literally every industry in the world now is being swamped by data. 80 to 90% of that data isn't being used, is lost within milliseconds of when it's collected, or is put in deep storage and never taken out and analyzed. And the cost, again, of not leveraging that information is off the charts. So this system that, again, we demonstrated a first generation, really prototype system back in February 2011, was the beginning of what I think of as this cognitive era of computing. It is not a system that we reprogram. It is a system that we feed better data. It is not a system that only knows what we tell it. It's a system that learns over time based on a feedback loop of decisions it's made and outcomes that it's seen. And we saw the very early stages of that. Now, at this point in time, in 2011, the system was great at natural language, which is a big chunk of the unstructured data that the world is generating. But beyond that, imaging data. The system was essentially blind at that time. It had no ability to take signal processing from the Internet of Things. These are now all capabilities that we've given the Watson system. So that's about the machine, but I think we need to talk a minute about what is going on between the human and the system here. Well, we know that we humans are excellent at some things. We have certain attributes in the way we learn, the way we look at the world, our own cognition, our own reasoning. When we look at what machines are capable of doing, it's also a very interesting set of capabilities, often used obviously for their mathematical precision, but that's no longer what these machines will be important for. And in fact, I would argue that it's this combination of human and machine which is the magic. It is the magic. In fact, there's been many studies that have shown that human plus machine will always beat a human or a machine at almost every task. And we have seen this, we saw it early on with Watson. When Watson would hit a roadblock in its learning and a human entered the picture and taught it something, Watson would make a giant leap forward in its capability to understand. And we see the same thing in fields where we're now applying Watson, where humans will hit a roadblock in their reasoning, Watson is introduced, and then there's a giant leap forward in the human's understanding. So something special is happening at this interface, this impedance match between humans and systems, and that, I think, is where the magic begins here at the CISL Center and what we're going to try to achieve. Human plus system interacting in totally different ways. What is a cognitive system? I would argue sort of at its simplest form, it's a system that learns at scale, reasons with purpose, has an objective, some defined objective, and interacts with humans in a natural way. Now that's easy to say, tough to do, but I think that's what the goal is here. Scale, reasoning with purpose, and then interacting in a very natural way, which speeds up this human plus machine process. So what is possible then? What can we rethink as humans in our lives and in our businesses? A few examples, and I'll start with a very simple example. Rethinking call centers. How many people are happy with the responses they get when they go into a call center? None. What if, not replacing the people in the call center, but what if Watson was available to help those people in the call center? Already being done. Many times, many insurance companies, retailers that you call the help center, that person has access to Watson. Watson has read all of their records from that call center, all of their product menus, and in real time can help that call center agent. Simple, but very effective in the consumer world. Rethinking things as simple as sports in 2 dimensions. We're working with companies that are working on sensors in helmets and other body protective gear, taking that information and looking at the shock that's being encountered by those athletes and making real-time sense of whether that athlete is in danger or not. At the same time that's happening, Watson is at work with the fans in the stadium, looking at different perspectives of the game and different analysis of the athletes, looking for any changes of behavior. So Watson, again, active in something as simple as sports. Insurance, very complicated field, but again, one that was ripe for us to introduce cognitive computing or Watson in. Today, with with a large insurer in the United States, if you go online and start applying for auto insurance, you will be talking to Watson. Watson will be helping you through that application. Watson has read the insurance laws in all 50 states, has read all of their policies, knows your preferences, knows your grouping, your demographics, and helps you through that process. Because it's well known, if you can get through that form, it's more likely that you will buy insurance and stay with that company. And this company that's doing this has seen a dramatic improvement in their sales because, again, the interaction has changed. In oil and gas, I talked about the platforms. More importantly, and this comes very close to what we're trying to do here at the CISL, oil and gas companies now, as I said, the cost of not knowing where to drill is huge, $200 to $300 million per well, and they only get it right about a third of the time. Tremendous, tremendous waste. And then when they get it right, they don't always pump the oil at the appropriate rates. We are building with Repsol in Europe a cognitive environment, a decision-making environment where they not only are looking at massive amounts of seismic data, but also business data, geopolitical data. Where should they be bidding on oil reserves in the world? An exact analogy to what we're going to be doing here at the CISL. Rethinking healthcare. One of the largest sets of data in the healthcare industry is in medical images. It's probably 2/3 to 3/4 of the health data. But as I said before, in 2011, Watson, in a sense, was blind, could not understand an image. Today, Watson has the ability to understand medical images and work side by side with a radiologist to understand that image. Why is that important? Well, typically a radiologist sits in a dark room all day watching thousands of images come by and has less than a minute to make a diagnosis. Fatigue, bias, what did I see last? Misdiagnosis. Watson can work with that radiologist to improve the diagnosis and hopefully save lives. President Jackson mentioned genomics. Everybody says, well, we've mapped the human genome, it's over. No, 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 no. It's just begun. It's just begun. We have so far mapped very few individuals' human genomes. Fortunately, the cost is coming down, but we hope to be able to now use Watson to make sense of the massive amounts of information, not only as we map our own human genome, but as we look for answers in the pathways that cause mutations in certain kinds of cancers. We have 14 universities we're collaborating with around the United States and in North America to map this knowledge of individual mutations in individual cancers, individual tumors, and individual people to find better therapy for those cancer patients. And one that really excites me, and again, President Jackson spoke about, is education. I think we have a chance to finally fundamentally change the way we educate our children as well as our adult population in the work environment. Because for once, we have the ability to not only present material, but really understand how every individual is learning and dynamically adapt that learning to the individual at that point in time. That's a capability we've never had before. We've had to educate the average and try to, also educate the extremes, but now we're down to an N of 1, an individualized education. I think this is going to fundamentally change education. And so lastly, I would talk about and modify my earlier statement and say that, yes, it's all about scale, reasoning with purpose, and interacting with humans naturally. But I think interacting with humans at scale, at our scale, is going to be a game changer, a game changer. And that's what this CISL is about. Now, we didn't wake up yesterday and decide, well, this was a good idea. We had been in IBM research experimenting with this for some time. Soon after the Watson event, we started building rooms and environments in our research labs that had all sorts of cognitive capabilities trying to monitor what was going on in that room and bringing cognitive computing to the people that were in the room. Many of these sort of small experimental labs. About 2 years ago, we moved to very large, high-resolution screens and walls where humans could interact and visualize data and try to interact with the Cognitive Watson system. And we started to see changes in behavior of the humans that were interacting with this data. So we took the next step up and built a small immersion room down in New York City where we can surround small groups of people with the data and literally interact with and have dialogue with Watson around the data and the information and start to make some decisions. It was at this point that we decided that we're onto something, but we needed a bigger platform, a place where people were working on these immersive technologies and where we could do it at scale. And that is what led us to conclude that Rensselaer, the MPAC facility here, and the laboratories in this building were a perfect setting to now explore this human-machine interaction, but at scale, with groups of people. We know what happens when small groups interact with Watson, but we don't know what happens. What are the dynamics as large groups of people interact? So this trend over the past several years is what led us to conclude that we needed to be here at Rensselaer in the MPAC. And then I'll just conclude with thanking Rensselaer, thanking President Jackson. This has been an incredible partnership. From the design and build of our highest performance supercomputers, as you heard earlier from President Jackson, to the use of those systems in many of the world's toughest engineering problems, to the initial work on Watson, to the students who graduated from Rensselaer and came and were part of that initial team that visited me in August of 2007. Rensselaer has been a golden thread through all of these activities. And we look forward to the next major stage of our partnership in cognitive computing at scale that I think will change the world. Thank you very much.